Hey, what's up, guys? How's it going? In this video, I want to go through LeetCode number 1277, count square submatrices with all ones. And this question was asked by Google and also Amazon, so mostly from Google. And we will apply two approaches to solve the problem. This one is the brute force, which is not the ideal solution, but it can give us the intuition. And after we have the brute force approach, we can build a point on top of it, and then we can have a dynamic programming approach, which is more efficient. First, let's take a look at the problem that we are given. So we have a n by n matrix that consists of 0 or 1s, and we need to write a function to return how many square submatrices have all 1s. So let's say if we are given a matrix like this, and the function output should be 15. So we have 10 squares of side 1, so it's each individual one. So 1, 2, 3, and we have total 9 in here, and plus 1 in here. So we have the 10 ones with a side 1, because 1 is by itself. And we have 4 squares of side 2, and side 2 is this one over here, and this one over here, and this one below here. This is the first one. This is the first one. This is the second one. This is the third one. This is the fourth one. So they are all overlapping, but they are still considered side 2. Side 3 is this bigger matrix. So yes, we have 1 square of that. And the total number of squares is 10 plus 4 plus 1, which is this the sum of the total squares, and this should be the function output. And let's take a look at the second case, where we have a matrix like this, and we have 6 squares of side 1, so this all the individual ones. 1, 2, 3, 4, 5, 6, and then we have 1 square of side 2, which is this guy over here, this smaller matrix. So and then we don't have a square of side 3, because there's zeros here everywhere. Not everywhere. This place, and this place. So we have the total number of squares is, equals to 7. Let's try a brute force approach to see how this works. And by the way, so feel free to pause the video at this point and then have a try by yourself. So let's take a look at the brute force approach. And by the way, the brute force approach is not accepted by LeetCode because it takes too long. But it's good to build the intuition behind it, and then there will be a stepstone for the next dynamic approach. And again, so the code will be leave in the description down below. So let's take a look at the first approach. We have some so again, the brute force approach works, but it's just not very efficient, and because it takes a lot of runtime, that's why it's not accepted by LeetCode, but it works. So let's take a look at it. So we first have some of the initial variables to be defined, and number of rows, and then number of columns, and then we just take one of the rows and then measure the length of the column. And then we have the maximum size that is possible. So if we minimum of the number of rows and or the number of columns. So let's say if the number of rows is 3, number of columns 2, and the maximum size we can do is 2. And then we have the first subsquares, submatrices with size 1s. So they are all individual ones. And so how can we account? So those are the easiest, because it's just very trivial. We just sum all the ones in the entire matrix. So this is how we can do it. And the initial total number of squares is equal to number of squares of size 1. This is our starting point to jump off. And then the rest is pretty pretty straightforward. And we checking the order size. We will look at this helper function later, but let's look at this for loop first. So we check on order size, and the size will be starting from 2 because 1 we have already checked it. So that's why we check. We starting from 2, and then the maximum number size plus 1 because the range that's not incorporating the last element. That's why we need to add 1 on top of it to make sure that we are looping through the max size. And for all the rows, and then we are looking at all the rows using enumerate, and we're getting the row index and then the row itself, and then we fill that row, which will be the input for the next for loop, and then we loop through all the columns, and then again we use enumerate, and then we check all. Basically, we're checking all the elements, individual elements, and we running this function if check square. If that's returned a true, and the total number of squares will be adding 1 on top of it, and the input for that will be the indexes, the row index, column index, and the size that we're looking at. So it can be 2 size, 3 size, and 4 size, etc. So basically it's doing this. So the checking square is checking is consuming the row index and the column index, and then the size that we're looking at. In this case, we're looking at size of 2. In this case, we're looking at size of 3. Also, we are given we are giving the index, the starting index to this function, and then it will have a function and loop through, and also the for loops to look at is that satisfy all the ones to make sure that it's a square. So let's take a look at the check square, and for the row offset and the column offset, and then we loop it through from 0 to the sides. So let's say if we have a size of 2, and then we will look. The size of 2 will be starting. The offset will starting from 0 to 1. We look at for example, when we check on this guy over here, the row offset will be 0, but the column offset will be 1. And here, the row offset will be 1, but the column offset will be 0. And in this one, both the row and column offset will be 1. That's why we're checking all the individual elements within that all the surrounding cells. And this is basically we are checking. This condition checking to make sure that we are not going off the edge, going off the boundary, and to check that if that is equal to 0, and then we stop this entire function, just return the false to save some runtime. If we keep going, and if this one condition is not hit, if this guy is not hit, and then we will return a true at the end. That means we checking all the surrounding cells, and this condition is not hit. Or if that hits a boundary, and then automatically and stop this function, and then we return a false. So this is the brute force approach, and as you can see, it's very inefficient because if we look at the size of 2 and look at the size of 3, there are a lot of duplicate work, right? So for example, when we check on the size of 3, and this one has 3 cells have been checked when we were at size of 2 already, and then we check it again for the goal of size of 3. That's why whenever there is a duplicate word, and the time complexity will increase exponentially. That's why it's not very efficient. And one way to we can solve this problem is to apply a dynamic programming to save all the intermediate steps to make. And for example, this checking has been done before. That's why we can save the work, and then when we perform the next layer of checking, we don't need to check this one anymore. And we save the intermediate step and to reduce the duplicate work and to increase the efficiency. Let's take a look at how that can work and in the code implementation. So which is a modification of this brute force approach, and let's take a look at it. When you scroll down here, this dynamic, as you can see, this dynamic programming approach, and as you can see, a lot of variables are the same as we defined before, and the total numbers squares is the same. However, we have one new variable that keep track of the submatrices we have seen earlier. So this is how we can save the intermediate calculation. This is the key for the dynamic programming. And at the beginning, we just save a copy of the original given matrix. We just save a copy of it, and this is how we can do it and use to list comprehension. And then this is the for loop that we come across before, and it's still very similar as you can see. And this check square is how we can modify it. Let's take a look at it. So this row index and column index looping is still the same as we saw in the prior for loop. And then this checking will not be performed unless the prior side is a complete square. This is what's going on in here. So in this case, let's say if the prior side, the prior square, is not a complete square, and it won't perform the checking in here. It won't perform this checking because there's 0 in here, and this is not a complete square of size 2, and that's why it won't perform. The checking in these edges, and this is how we can save a little bit of runtime in there. And this is what this condition is doing. So let's say if we are checking the size, currently size is 2, and if the prior record is not a complete not a complete square. So let's say if the prior record is not a size of 1, and this one, then the rest would not be performed. If it is 1, and then we will check the square, and this is where we can reduce a lot of runtime. And so let's roll up this again. So let's say if now the size is 3 that we're looking at, 3 for the square, and this condition is satisfied already before we run in before it goes to the check square, means the prior square is already a 2. It's a complete square, so we don't need to check this anymore. What we need to do is only check these edges, these boundaries. And how we can do it is to first look at the bottom right corner to see if this is a 1. If this is a 0, we automatically no need to check the rest. And this is what this statement is doing. And then we can check the row offset, which is, so this is the bottom right corner to check if that's equal to 1. If that's equal to 1, we can perform the rest. If it's equal to 0, no need to do the rest. And then we go through the row offset along the row, and then we can do the column offset that checks the columns to make sure that to see are there any zeros in there. If that is 0, automatically stop this this function and then return and then return a false. If none of this false, none of this return false get hit, That means everywhere are ones, and then they will return a true, and then the record, the site record will update by the current site. So it will go from 2 to 3. In this case, it will go to from 2 to 3. And advantage of this one is and there is not a lot of duplicating work, because we go from, let's say we go from the size of 1 in here, and then it expand to the size of 2 by checking these two borders, this guy and this guy, by this row offset and column offset, and also bottom right corner by this if statement. And after that, we have a size of 2, and we save in the sub square site record in this matrix. And then when we check the size of 3, we only check the borders again, and we will save the work if it is. If it is not, we will not even bother for the pink one, because we have this condition over here. If it is a size of 3 square, and then we will continue the evaluation for the size of 4, and by checking these edges. So, and this solution has been accepted by LeetCode, because it's much faster than the brute force. And even though they produce the exact same result, but it's much faster. And yes, so this is my solution, and I hope you like it. And if you do, please hit the like button and subscribe to the channel. And I will see you in the next video. Thank you.